So now let's take a example. Okay, we'll take one fun example. Okay, this example is due to a person called Joe Keller. Okay, so it's a fun way for us to kind of absorb the concepts that we have spoken about in this lecture, and the premise of this problem is how to live longer. Okay, so let's look at this fun thing. So how to live. Okay, so what is the information that I'm going to give you? I'm going to give you some information. So given, so HR is heart rate. Okay, so heart rate of a person at rest, (80 beats per minute). Okay, the heart rate of a person exercising. Any guesses? Okay, not bad. Let's take 120. Okay. So now let us say that everyone is born with a fixed number of heartbeats. Let us say. Okay. You just don't know how many they are, but everyone is born with a fixed number of heartbeats. Born with. Please don't get depressed. Okay. So the question is, can we figure out what fraction of the day we should spend exercising? We'll come to that. What fraction should we? So immediately I saw the answer as 0, which is the correct answer given this information in the problem, right? Can anyone see why? Can someone else tell me why should the answer be 0 for this problem? Because exercise increases the heart rate. If I have a fixed number of heartbeats, I'll exhaust them sooner, I'll die sooner, right? But so the person who never went out for exercise, who only stared at their Instagram reel, will answer 0, because you know what else is there, right? So, but intuitively, what was the problem that was being solved? I mean, you didn't do it this way, you just automatically said it, but can we form an objective function for this problem? So let us say x is the fraction. Okay. So in a day or in a minute, it doesn't matter, how many heartbeats are gone if I am exercising a fraction x of the time? How many heartbeats? Let's call that f of x. So I am exercising a fraction x of the time. When I am exercising, what is my heart rate? 120, right? So 120 into x, these are the number of heartbeats during my exercise time. And when I am not exercising, how much am I losing? 80 into 1 minus x. Okay. Now what kind of a, we can even draw this, right? As a function of x, what will this be? It's a straight line, right? And you can, without even doing the calculation, you can see that there are two endpoints, x equal to 0, x equal to 1. Again, I am doing this intuitively. Where did I get x equal to 0 and x equal to 1 from? Constraints. We will call them common sense constraints, because heart rate can't be negative, can't be greater than 1, right? Then I look at the solution at 0 and I look at it at 1, and at x equal to 0, it's going to be 80, at x equal to 1, it's going to be 120. Obviously, 80 is less than 120, so I will choose x equal to 0, right? Now I say that, hey, wait a minute, this doesn't make any sense, because exercising seems to do something. People who exercise seem to live longer, and I mean, by and large, who can tell, but yeah. So in the language of optimization, where did we mess up? The objective function, yes, of course in the objective function, but what in the objective function did we not get right? Parameters means variables. So x is there, what? So again, so okay, I am getting the correct answers. This is, we have made a modeling error. We have modeled the objective function incorrectly, right? So there is a modeling error because we know that a person who exercises and then comes to rest versus a person who only watches TV and comes to rest, there is going to be a difference in the heart rate. We have seen that. I mean, if you haven't, then you can observe. Those athlete friends of yours, you can see if you take their heart rate, their resting heart rate is actually much lower than it can be. I mean, 50 for example is common. In fact, that's on a side note, I used to have some athlete friends who were like extreme athletes, and their problem was because their resting heart rate was so low, they would sit in class and just go to sleep because it just shuts down. It's not that they were bored or anything, just not having activity, they would just go to sleep. The heart rate would go so low. So don't exercise that much. So modeling error over here. Okay. So I'm going to model the resting heart rate a little bit like this. Okay. So let's write it like this. Let's start with the intuition that more I exercise, resting heart rate should be lower, right? Okay. So more I exercise corresponds to our variable x itself, right? So this is x. Okay. So when x is small, okay, I'm going to call this resting heart rate, instead of 80, I'm going to call it by some other word. Okay. So g of x. If I don't exercise enough, my resting heart rate, let us say, is 80. Couch potato. Okay. Potato. Spellings are terrible. Is it correct? No E. Okay, no E. X is large. If I exercise a large fraction of the time, let us say 50. Okay. You notice I am making some kind of assumptions over here. Actually, what should I be correctly doing to get these numbers? Where should I be looking? Survey is one thing, experiment is one thing, but if I am a little more smarter than that, what will I do? Because if I survey people who are living on the top floor of the hostel, I will just get 80 everywhere. If I survey the inter-IT team, I will get 50 everywhere. So survey is not really a good idea. Interpolation, but I am interpolating between bad examples then. If I interpolate between 80, 80, 80, 81, then what is the smarter, intelligent way of solving this problem? Come on guys, do it on ourselves. Okay, I don't know if that's better or worse. Everyone's heard of Google? How about I go into Google and type Journal of Sports Medicine? Guess what? There are scientists who do this for a living. I can just get their data, no? Correct, right? So I can look up a place where experts have done this work, right? So this is another thing that as engineers we have to learn. Do not reinvent the wheel. Do not do it on yourself to start with. Tempting as it may be, right? So go to the right places, because what are you trying to fix? Remember, what was your starting point? You wanted to fix modeling error, right? You don't want to replace modeling error by yet another modeling error, right? So that's an example. So let us say that I do, I did this exercise, and turns out that g of x is something like this. It's possible when x is small. What is the value of this function? 80, right? When and x is large, 50, right? So this is kind of, and it's smoothly, we expect it to be smooth. We don't expect some crazy stuff to happen, right? We expect it to be smooth. Now this is, again, this is, you can almost call this as art, right? I mean, this is coming from, this is not coming from you. This is coming from some other engineering or sports discipline, right? So you have to take that with a grain of salt. This is what you got, right? And now with this, what is my objective function? F of x is going to be, when I am exercising, I am still taking it as 120 hearts, beats per minute, okay, and would you agree that this is the correct new objective function, right? When I am exercising, it's 120. When I am not exercising, I have my heart rate, and my heart rate is given by this function g of x, okay. Okay, so now what? I've done, what have I done? I've done my problem model. What is the next thing I do? Solve it. In this simple case, solving means what? I want to minimize or maximize f? This is number of beats in a day, right? I want to minimize it. So I want to, so this is model. Now I want to minimize it. You could solve this problem in class 12. What would you do? F dash x equal to 0. Okay. Does this look like a nice problem that I can run, take the derivative and solve? Okay, I am happy to hear yes. Right? What is it? It's a linear function, it's an exponential function. I can differentiate it in my sleep, right? I'll get the answer. Now, I'll give you the answer since I worked it out. It's a believable number, right? 53 minutes a day. So you can work out, I mean, I'm converting the fraction to minutes per day. I got some number, multiplied it by whatever to give you a number which is 53.7 minutes a day. So when you hear from doctors' advice to old people, they say, "Na, walk for 1 hour in the morning, evening." I mean, it's based on stuff like this. It's not just come out. I mean, it may have come from some WhatsApp forward, that I'm not discounting that, but scientifically, how you want to arrive at this stuff is like this. It's not super complicated. Model the problem intelligently, solve it, and make a prediction. And you can kind of do this for any problem, really, right? The trick is to model the problem with appropriate complexity. If I modeled it with not enough complexity, my recommendation would be a couch potato, because that way you optimize your heartbeats. But this is a little bit more, right? So the more effort you put into modeling, the better solution you get. The price you may have to pay is more complicated optimization algorithm. Everyone is happy with this solution, but we didn't do one thing. What is that one thing? Check for optimality, right? How do you know that this f prime x equal to 0 happens both at maxima and minima? How do you know that this is not the solution to die soonest? It could be. So what should we do next? So f double dash x should be you can check it, and if it turns out to be greater than 0, then next what will come? FDA approved or something, right? So that's how this happens. Okay. Now you can see clearly that this was a constrained optimization problem, although when you solved it, you did not write over here such that, did you write this? You didn't write it, right? So this is you're still coming out of class 12 kind of solution strategy, do something, set derivative equal to 0, and what is you're relying on luck, hope, whatever, right? So in this case, it worked out that you got a solution which was fine. Okay. It may not always happen this way, and we will see this in the second half of the course, that it may not always happen, and you have to, there is a proper framework, kind of a generalization within calculus which allows you to work with constraints in the optimization problem. Okay. So All right, I think that's as far as I have with regards to introduction. Okay, so any questions on what we have been speaking about so far? So you've got the basic idea over here, right? Modeling the problem correctly is one of the most important parts of an optimization problem, and unfortunately this is the place where most engineers get tripped up, because they're in a hurry to solve the problem. You don't model it correctly, you get a ridiculous answer like 80, right? And various such things can happen. Okay.